Hey everyone. Welcome to the first of many things that I will be recording. So the first thing that I wanted to go over was a little bit about chapter 8 and some of the more important bits. So chapter 8 is all about hypothesis testing, which is similar to the hypotheses you make for all of your science-based classes, because math is yet another science-based class if you think about it. So what we're going to be looking at is testing whether or not a statement is true and assigning a hypothesis for if it's equal to what we're testing for, or if it's not equal to, less than, more than, whatever the other parameter is. So a hypothesis in statistics is a claim or statement about a property of a population. So remember, we're thinking broad scale about the entire population, and we're usually basing that off of a specific sample. So remember the difference between your, I have hiccups. The difference between your population and your test or your samples. Remember, for our population, we're usually using Greek letters, and for our smaller samples, we're using our English letters. So remember, if you're having a hard time differentiating between the two. All right, so moving on into hypothesis tests. So all we're doing is testing for the significance of each of our hypotheses, and that's just looking at the procedure for testing a claim about a property or a population, which is similar to what you do in science. You either prove your hypothesis true or you prove it false. In math, we just create two hypotheses, one to be equal to what we're measuring, and one for what we believe the outcome should be if it's not directly equal to it. So, let's try and move. They give us an example right away. So we're looking at the majority of consumers that are not comfortable with drones delivering their packages. So they tell us 1,009 consumers were asked if they are comfortable with having drones deliver their purchases, and 54% of them, or 545 of them, responded with no. So using P to denote the proportion of the consumers not comfortable with drone deliveries, the majority claim is equivalent to the claim that the proportion is greater than half. So that's something that's going to keep coming up, is that if we're looking for the majority of people, it has to be more than 50% of those people, which makes sense. So how we're going to set these up is our P is going to be greater than 0.5 or 50%. So we're going to use that as our symbolic expression for our claim. And they're going to be asking for symbolic expressions or symbolic forms. And that's all they're looking for, is putting what they gave you into a simple formula as opposed to writing it out in words. So thinking more from a big picture, we have the claim that the population proportion, or P is greater than 0.5 or 50%. Among 1,009 consumers, how many did we need to get a significantly high number who are not comfortable with drone delivery? And that's just proving outside of what would be a normal parameter. We want to see what would be a significantly high number of people who are not comfortable with drone deliveries. So if we were looking at our results, we had 506, so about 50.1 would be barely more than half. So 506 people is clearly not a significantly high number. If you have just over 50%, that's not going to be a significantly high number. But a result of something like 1,006 people out of 1,009 would be a very significantly high number. So we always want to be comparing what we're doing to see if something is significantly high or significantly low, if it's an alternative. Let's see. You're also going to see the phrase that all of you love, which is use technology. So I'll be making a couple, I guess not lectures, but example problems and how to go over them in StatCrunch and hopefully even some in Excel. So we are going to be using our computers a lot for some of these problems, but I'll be able to show you how to do them out by hand also, because I think that's also a very important skill. So here's just some examples of what it would look like. The two I normally use would be my calculator, because the proportions are already built in, and StatCrunch, obviously, because they're already built in there as well. But you can do some of these in Excel, and I'll go over some of those with you as well. So they're giving an example of using technology and how they display your test statistic and your p-value, but we'll talk more about that later. And significance. So going back to what our hypotheses are. So we're going to have two different hypotheses. We're going to have our null hypothesis, which is our first one, and it's just denoted by this H for hypothesis, and we just give a sub of 0. And that's just saying that it's our null hypothesis. That's just what it's called. So it's a statement that the value of a population parameter, which can be your proportion, your mean, or your standard deviation, and it's going to be equal to some claimed value. So there's going to be a number inside our problems that we're given, and we're just setting up our null hypothesis to just plainly be equal to that claimed value, because that's how we're going to build the rest of our problem off of. So we don't just have our null hypothesis, we also have our alternative hypothesis. So you can see this denoted in two different ways, either an H sub 1 or an H sub A, either capital or lowercase, it doesn't really matter. It's just telling you it's your alternative hypothesis. But they also like to say, since our null hypothesis is H sub 0, our alternative would be H sub 1. And it's just a statement that the parameter has a value that somehow differs from the null hypothesis. So for the methods of this chapter, we're just going to be using symbolic forms for the alternatives. So either less than, greater than, or not equal to. And since our null hypothesis is always in equals, this is just the alternative to what's happening. So if our value or our problem isn't equal to a specific value, we're going to be looking at the alternative if it isn't equal to that. So if we were looking at if something is greater than, our null hypothesis would still be equal to 0, but our alternative, we would then use greater than. So hopefully these will get a little less confusing once we use them more, but just knowing the difference between null and alternative. Your null is just how we're setting things up to be equal to our specific claimed value. And our alternative is what we think would happen alternatively if it wasn't just equal to that value. So there's also this really nice table or flowchart, I guess, for how to identify your claim and set it up in symbolic form, and then how to find your p-values or your critical values. So definitely check this out. This is already in the slides that are posted. So moving on, we're also going to be using confidence intervals still. You can't get away from them. I know they were kind of a struggle for chapter 7, but they're still here, and we're going to be building off of them. All right, guys, so if we're looking at creating confidence intervals, we want to look at them the same way. We're still using our alpha to find our significance level, and then converting it to whether we're looking at 2 tails or 1 tail. So I marked this down as one of the important slides. So using the original claim to create a null hypothesis and an alternative hypothesis. So step 1, we want to identify the claim that's being tested and express it in symbolic form. And all that means is, it was like we said in the previous slides, apparently it was more previous. Our symbolic form is just putting our proportion, our mean, or our standard deviation into a claim. So if we were looking at the probability of most people, we would be looking at our P being greater than 0.5 or 50%. So if I were to go back down, if we're putting step one, looking for this to be in symbolic form, we would just be stating our hypothesis or how we're measuring our hypothesis. So step two, we want to give the symbolic form that must be true when the original claim is false. And that's just our alternative. So if we're looking at our hypotheses, our alternative, what on earth is happening? Our alternative hypothesis, or H sub 1 or H sub A, however you want to write it, is the one not containing the equals. So our alternative to if our claim is being met exactly or alternatively. And then our null hypothesis is the symbolic expression that the parameter is equal to the fixed value being considered. So if we're measuring for something to be most people, we would be looking for more than 50%. So our null hypothesis would be equal to 0.5 or 50%. And our alternative would be greater than 0.5 for more than 50% or to contain most people. So if we were to look at another example, they tell us about drone deliveries again. So they give us the given claim that the majority of consumers are uncomfortable with drone deliveries. And then we can look at supplying our steps. So for step one, we're identifying the claim. And like I said previously, if we're looking at the majority of people, most people, they like to phrase it a bunch of different ways, but if we're looking for most people and they don't give us a exact proportion, we're just going to be using 50% because that's going to be our threshold to separate most people from less than most of the people. So we want to be setting up our proportion as being greater than 0.5 or greater than 50%, giving us more than half. So for step two, we'll give the symbolic form. That must be true when the original claim is false. So if our original claim is P is greater than 0.5, then what's false would be P is less than or equal to 0.5. So for step three, we're going to put those two parts together to create our two hypotheses. So for our alternative hypothesis, we're going to be using the two symbolic expressions. So our P is greater than 0.5. All right, guys, so we're going to be identifying our alternative hypotheses and our null hypothesis. So using the symbolic expression, we're going to frame our alternative hypothesis, which is our H sub 1 or H sub A, with our proportion being greater than the 0.5 because we're looking for over 50% of people. So our null hypothesis, or just meeting our threshold where we have an equals, we're just going to set it up to be equal to our 50% threshold to get more people or most people. So moving on to step four, we're going to be looking at the significance level, which we use with our alpha, which we used previously in chapter 7. So we're going to still be using it for our hypothesis testing, and it's the probability value used as the cutoff for determining when the sample evidence constitutes a significant evidence towards the null hypothesis. So by nature, the significance level for alpha is the probability of mistakenly rejecting the null hypothesis when it's still true. So our significance level is the same as our alpha that we were talking about in chapter 7. So also known as our critical values. So usually we have 0.05, 0.01, 0.1, or 0.05. Oh, it has 0.05 twice. That's really strange. We can also have 0.025 is another common one. You sometimes don't see it as much when we're just looking at hypotheses. So there is a step 5 in all of this. So the last thing we're going to be doing is identifying our test statistic, which is relevant to testing or determining your sample distributions. So it's things similar to what we were measuring before. We still have our z, t, and our chi-squares, depending on what we're measuring. And I'm going to send you guys a little cheat sheet to remember which ones to do when, and it's also included in the PowerPoint. My computer's stuck. There we go. So this is going to be your holy grail, I suppose, for knowing when to do what. So if you're measuring a proportion or a p, you're going to just use our normal z, and you should have all of the appropriate information to use this formula. Mean, we have two options, and is similar to chapter 7 if you know your sigma or not, which is just your standard deviation for your entire population. So if it's not known, we're still going to use t, and if it is known, we're going to use z. And if we have a standard deviation or variance, we're going to be using our chi-squares, which is exactly the same as chapter 7. So going back to our drone deliveries, if our claim is that our proportion will be greater than 0.5, we're going to be using a normal distribution, and provided that we are having all of our requirements met, we can keep moving forward to step 6, which is finding the value of that test statistic and the p-value or critical values. So a test statistic is a value used in making a decision about the null hypothesis. And it's found by converting the sample statistic, such as your p-hat, your x-bar, or your sample standard deviation, which is S, to a score such as your z, t, or chi-square. And that's all with the assumption that you're using the null hypothesis to be true, which our null hypothesis is the one that we set up just being plain equal to what we're measuring. So if we're looking at our claim, so if we were to use the same drone example that we were talking about previously, they gave us the total number of people they surveyed as 1,009, and then gave us an X, or what we're looking for, or the number of people who answered no, as 545. So we can actually solve for p-hat by just using our x over n like we normally do, the thing we're looking for over the total. So we can look and set up our null hypothesis, since we're looking at our, our proportion being greater than 0.5. We have to get over that threshold of the 50%. So if we're working with that assumption, and we can solve for q as 0.5 also, because we're just doing 1 minus p. So we can actually plug in with all of our information into our z test statistic formula to get a z-score of 2.55. So we'll also be looking at critical regions, which is the area corresponding to your test statistic. So it's similar to stuff we've talked about before. So now we're just looking at whether something is a two-tailed, a left-tailed, or a right-tailed. So if something is two-tailed, the critical region is in the two extreme portions, or the tails. So either end. If it's left-tailed, then the critical region is on the extreme left. And if it's right-tailed, it's on the extreme right. So we also have a p-value method. And so when we're doing a hypothesis test, the p-value is the probability of getting a value of the test statistic that is at least as extreme as the test statistic obtained from that sample data, assuming that our null hypothesis is true. And our null hypothesis is the one that's equal to our threshold. So if we're using the same data that we were using before, we would calculate our z as the 2.55, and it would have a normal distribution area of 0.0054 to the right, and our p-value would be that 0.0054. and we'll go over how to calculate our p-values in the follow-up questions after the survey. So you can also find it here in this flowchart. So depending on which test you're doing, and is your test statistic right or left centered. So this is also a very helpful flowchart. And it's also important to remember that your p-value is different from your p, which is also different from your p-hat. So your p-value is the probability of a test statistic at least as extreme as the one you found. Your p is your population proportion, and your p-hat is your sample proportion. So you'll also have your critical value methods. So our critical values in a hypothesis test are separating the critical regions, so where we reject the null hypothesis, from the values of the test statistic that do not lead to the rejection of that null hypothesis. So if we were looking at our example we were looking at before, the critical region is the shaded green region, and the figure shows that the significance level is alpha equal to 0.05. So the critical value is z equals 1.645, which, if you guys remember, our critical values can be Googled. They're in the previous slides. Whenever you're dealing with a critical value of a typical alpha, it's something that is used very frequently and you can find very quickly. So always remember that. Don't spend too much time trying to solve for those if you've already know them. So step 7, we want to make a decision to either reject our null hypothesis or fail to reject. So you would think that it would either be true or false, but instead we use reject and fail to reject. So reject obviously means untrue. Fail to reject means that it is true. It's a little confusing with the wording, I get that, but it's just how we phrase it. So our criteria for either failing to reject or rejecting, we use our p-value. So if our p-value is less than or equal to our alpha, we're going to reject our null hypothesis. So they also like to throw this one out there. If the p is low, the null must go. So if our value is less than or equal to our alpha, then we're going to be rejecting it. But if our p-value is greater than our alpha, then we'll fail to reject it and treat it as if it is true. So for step 8, we want to restate that decision using a simple non-technical term. So without using our typical terms, we want to state a final conclusion. So for our drone example, there's sufficient evidence to support the claim that the majority of consumers are uncomfortable with drone deliveries, which is supported by our data. So if you ever need help wording it, you can refer to the table in the next slide, which would be really helpful. You just want to make sure it's supporting your original conclusion. So depending on the conditions, if your claim does not include inequality and you're rejecting, so really you're looking at whether or not you're rejecting and which part of the claim you are supporting. And it's all dependent on what is actually being measured and asked of you. So looking in terms of accepting or failing to reject, we should say that we fail to reject the null hypothesis instead of saying we accept the null hypothesis. Because again, we like to use the failing to reject or rejecting. We want to make sure the word reject is in the phrase.